Thank you for the introduction. Good morning, everyone. I'm Wenbo from Ant Group, the blockchain division. Today, I'm going to present our work, the flexible advancement in asynchronous BFT consensus. This is a joint work with Shanghai Jiao Tong University. This work is supported by the Zen platform. Zen provides the comprehensive technology and ecosystem of Web3. Now this is the content of my talk. Firstly, I will introduce some backgrounds and case study of the blockchain consensus from our production system. Then I will point out the problems of the classical asynchronous consensus. Then I will explain our work, the flexible advancement, and my Tumblr algorithm, followed by the experiment result. Then finally, I will conclude my work. Consensus is the core component in state machine replication and blockchains. It ensures that replicas must agree on the same execution order of client requests. No matter in a distributed database or in blockchains, they both require the safety and liveness. However, there are also some differences. First of all, in blockchain, the nodes, they do not trust each other. So the Byzantine fault tolerance is, we must consider that because a selfish node may have the motivation to cheat and to break the system. Second, that's why the BFT is proposed like 40 years ago, but is only applied in real systems since recent years when blockchain comes out. Secondly, the nodes of a blockchain, they can be arbitrarily deployed everywhere in the world. So the network is unstable and asymmetric, unlike in the data centers. And thirdly, blockchain normally does not have the facilities like a gateway or a load balancer. So all of these features, they call for carefully revision of the BFT consensus in blockchain systems. Here we have 3 cases to address the issue. All of them come from our real production scenario of Ant chain. In the first cross-border supply chain, the nodes are distributed unevenly in the world. So most of the nodes are in East Asia, but some are in other continents far away from the majority. And in the middle is the B2B market. The transactions are not that frequent, so low latency is preferred in this case. And the third one is a cross-border remittance case. Some e-wallet nodes are busy at serving the client's requests. There are also some liquidity provider nodes, usually big banks. They just issue much less requests for making a market. So all of these cases are real. It turns out that in an open, wide area network and so many complex cases, asynchronous consensus is a promising solution, as it has no timing assumptions, so that we do not need to tune the timeout parameter, and the nodes work in a leaderless manner, so that each node has the right to make its own proposal. So now we have a look at how the classical asynchronous consensus has a problem with the new system features of blockchains. We take a look at the BKR framework, which is named after the Ben-Or, Kamel, and Rabin. The first step is every node starts a reliable broadcast, or RBC for short, about its proposing requests. The RBC ensures agreement, but does not ensure termination. That means a node cannot wait forever if an RBC does not terminate, because the sender might be faulty. If the RBC sender is correct, the RBC must eventually terminate. For all terminated RBCs, every node inputs 1 to a binary agreement, or BA for short. The BA ensures both agreement and termination. If a BA outputs 1, it means the corresponding proposed request is committed. As said, a node should not wait for the unfinished RBC forever. So if n minus f BAs, they output 1. Then each node tries to abort the remaining RBCs by inputting 0 to the corresponding BA. Since BA ensures termination, after all the BAs have output, the whole consensus finishes. The committed requests are from the instances whose BA outputs 1. So in this case is request 2, 3, and 4. The above-mentioned steps are the consensus of a given sequence number. After this sequence number finishes, the system advances to the next sequence number. This is called the static advancement or fixed slot advancement, since every node has a dedicated slot per sequence number. In this fixed slot approach, we can see at least 3 issues. Firstly, every node must propose at every allocated slot, even if it has no requests at hand now. In that case, it sends an empty proposal, which must also go through the agreement, go through the RBC and the BA. That is a waste of resources. Secondly, if there is a slow or faraway node, it can easily be suppressed by the other fast nodes because the nodes they are competing for the same sequence number. We will see this in our experiment later. And thirdly, the agreement process, namely RBC plus BA, is less efficient and time-consuming. So all the 3 issues cause for a new consensus paradigm. That is the flexible advancement. And we design a timestamp-based consensus protocol named MyTumbler. Unlike the fixed slot paradigm, flexible advancement should allow every node to freely choose a position to propose. Furthermore, a node even has the flexibility to propose or not at all. An empty proposal should not go through the agreement, but should be quickly skipped and pushing the system forward. That is the basic idea, but this is not an easy task. The fixed slot has a benefit. Every node knows the existence of all the slots, as shown in the left figure. Some slots exist, but their results are unknown. Then the node knows to wait for the agreement result. This is called the known unknown. However, if every node can freely propose a non-consecutive agreement number, things become complicated. Because we have to ask, when is it safe to execute the committed instance? A node may not even know the existence of some slots, not to mention their results. This is an unknown problem. In order to safely execute a request TXI, the node has to ensure that all committed requests before TXI must be known, and no further requests ordered before TXI can get committed. To achieve this safety requirement, we first look at the agreement. What kind of proposals can get committed? It turns out that only if it is endorsed by a quorum of nodes, the proposal can get finally committed. In other words, if a quorum of nodes, they swear not to endorse it, it cannot commit it because of quorum intersection. Based on this observation, we have designed the pass mechanism to overcome the unknown issue. And that is the key concept of the MyTumbler algorithm. Nodes continuously send a pass message. It has 2 purposes. Firstly, it carries a set of proposals which is endorsed by this node recently. And this will let the others know about the proposal in case of they missed it. The second purpose is to promise a timestamp T. The node will not endorse any proposals ordered before T. You may notice that the 2 purposes, they exactly match the safety requirement listed on the right side. So now the first question is, when does a node to send the pass message? We require that a node should pass T only if n-f proposals after T from different nodes are committed. This is for the liveness consideration, and we omit the details here. So in this picture, suppose n-f is 3, so B4, B6, and B7, they are committed. So the node can send the pass message for T4, and it carries the endorsed proposals from B1 to B7. After a node receives the pass from the others, it may hear about some unknown proposals. Like in this case, it does not know B2 before, but now it knows. And because it has already passed T4, so it should not endorse it anymore. So it tries to abort it. So the final question is, when is it safe to execute the committed proposals? The answer is after a quorum of nodes past t, the node can safely execute until time t. The node should gather some proposals from the past messages. It waits for the decision of all the known proposals before t. And for the other unknown proposals, because a quorum promises not to endorse them, they can never be committed. So the node can safely execute now. So now we have the pass mechanism, we can further design the lightweight skip mechanism. When a node decides not to propose before t, it broadcasts a skip message for t. This skip is different from an empty proposal. It does not go through the agreement, so it is lightweight. This is only possible when we have the pass mechanism. Now the criteria to send pass should be slightly modified. There are m-f nodes. They either have their proposals after t committed, or they declare a skip t. Then the node can pass t. So far, we have the pass mechanism, and we have the lightweight skip mechanism. Finally, we can optimize the agreement part. So let's dig into the agreement instance. It is a reliable broadcast plus a binary agreement. We now give an abstraction of this combination, named the abortable reliable broadcast, or ARBC. We define the following properties, which is crucial to the correctness of the whole consensus. Namely, agreement, conditional termination, and strong validity. The strong validity, we have already used it to design the pass mechanism. The conditional termination says that if every node tries to abort, then every node can output, so that's why it's conditional. So with this abstraction, we can have a modular approach to optimize the agreement. For example, we have designed a fast BA to replace the original BA algorithm, and we further give a more efficient instantiation of ARBC with fast path called superma. Due to the time limit, I cannot go into details, but one thing is it can terminate in 3 message rounds in the best case, compared to 7 rounds in RBC plus BA. And this is because the superma, it can bypass the randomized BA if a quorum of nodes have the same inputs. And because this is an abstraction, so any further optimization in a modular way is also possible. So now we will show the experiment result, and this result is recognized by this artifacts evaluation and reproduced by them. So the experiment consists of up to 100 cloud nodes over 6 regions across the globe, and each node has 8 vCPUs and 32 gigabytes RAM, and the bandwidth is 5 gigabps, and every request has a 1,000 bytes size. We have chosen 4 other algorithms for comparison. Hot stuff is a leader-based partially synchronous consensus. Task is a state-of-the-art DAG-based async consensus. And then it's the classical BKR. And we also replaced the agreement in BKR with our superma to show the effect of this optimization. So the first test is in the asymmetric network, where there is a faraway node. So there are 3 nodes in East Asia and 1 in Frankfurt. We can see that in task, the Frankfurt node cannot commit its proposals at all. But my Tumblr and BKR, they are friendly to the faraway node. But when optimized with superma, BKR cannot make the Frankfurt node to commit either. This is because the 3 Asia nodes, they are too fast now. So they terminate their agreement while the Frankfurt node is still proposing. So now we test the unbalanced workload. Here we have 10 nodes, but only 1 or 3 of them have requests. The others are all idle. So we can see that BKR superma can effectively reduce the latency, but my Tumblr has the lowest latency because the skip is lightweight. It can totally get rid of the empty agreement. So the last experiment to show is we test the peak performance of all the algorithms. The left figure is the 100 node test. When BKR is optimized with superma, its latency reduces from 30 seconds to about 5 seconds. Also, outperforms the other algorithms in throughput. My Tumblr has further doubled the throughput to 130,000 TPS. So the reason is that under flexible advancement, every node in my Tumblr, they are continuously proposing, does not need to wait for the others. And most importantly, the agreement instances of in my tumbler, they are seldomly aborted. So the right figure shows the peak throughput with 4 nodes, 10 nodes, and 100 nodes. We can see that with 100 nodes, the performance of hot stuff degrades because it is a leader-based consensus, which becomes the bottleneck. Surprisingly, my tumbler and BKR, they all have an increasing trend of throughput when the node size grows. This is because in asynchronous leaderless consensus, the bandwidth of all nodes are fully utilized. Not only the leader is proposing. This also challenges the prejudice that asynchronous consensus is more complex and less efficient than partially synchronous consensus. Actually, asynchronous consensus they are quite scalable with a big group number. So to conclude, my tumbler with the flexible advancement is a new consensus paradigm. It enables faraway nodes to fairly commit their proposals and also has a lightweight skip mechanism. We also define ARBC abstraction as the building block of asynchronous consensus and gives an efficient instantiation supermar. The experiment shows that no matter in large-scale network, the peak throughput or under unbalanced workload or light workload, asymmetric network, etc., my tumbler always achieves the best performance. And as a final remark, this work is a part of the End-Chain Open Labs, and thank you for your attention.
Hi, I'm Suyash Gupta from UC Berkeley. Thank you for the talk. I want to ask a question. So if an honest node actually issued a pass message and rest of the honest nodes formed a quorum and they were actually able to proceed with the transaction, then how do you ensure that honest node which actually issued a pass is able to reach the common state?
Are you asking when an honest node sends this pass message?
Yeah.
Yeah, according to definition, when it has seen m-f proposals are committed after timestamp t, then it should send this pass message. Because if no correct node pass a timestamp t, then any proposals after this time cannot get aborted because they are all happy about this timestamp. It's not in the past, but it's in the future. So they will endorse it and making it to be committed.
But I thought the notion of using pass was you don't have everything for every slot, right? So there are some slots for which you don't have a request, and that's why you're issuing a pass message, right?
Not really, because you're talking about the skip mechanism and the agreement, the relation, right? The skip actually has nothing to do with these boxes here. It just helps the others to send this pass message. So the committed results purely are from this agreement part. So this box will tell you whether this is aborted or it is committed. But the skip itself does not create an empty box here. It just like a boost or give you a hint to pass some timestamp.
Oh, okay, thank you.
Hi, I am Rodrigo Rodriguez from IST in Lisbon. I'm curious, given that you have a real-world adoption of this protocol, did you previously use a partially synchronous protocol, and what were the pain points of the partially synchronous protocol that made you move to asynchronous?
I think the biggest issue is the performance, because we use the like traditional. You mean in our production system we use some traditional leader-based protocol. So when the number of nodes grows, then the leader becomes a bottleneck, because even if we have used some like hash to proposing only hash instead of the payload, but still that is asymmetric because the leader has also full utilized, used up its bandwidth, but the other nodes, they have an idle bandwidth, so we cannot make fully use of the bandwidth resource. So that's why we decide to consider the asynchronous leaderless protocol.
Hi, I'm Scholt Istvan, TU Darmstadt. So my question is a little bit going along the same lines, and I think to me it sounds interesting that you said, well, you know, many things can happen in this distributed system, and you chose an asynchronous model to kind of make sure it will work in any case. But can you give an intuition on the alternative being restricting the behavior of the nodes, right? I mean, it sounds like these are enterprise nodes or machines running in a cloud. You could also impose stricter requirements on, for instance, when they need to answer or what they need to provide in terms of, you know, deadlines on delivering messages. So was that a consideration to basically say we put more restrictions or requirements on what nodes can do? And if yes, then maybe can you tell us a little bit why that's not the way to go and why moving to this side of the design space made more sense for you?
I'm sorry, I didn't quite get the question, and could you please rephrase it a little bit?
Is it the audio, or because I hear myself in an echo? Is that the problem, or should I just rephrase the question?
Please rephrase it. Yeah.
Okay. So one alternative would be to say, instead of going to the synchronous model,
yes,
to set up stronger requirements on what the nodes have to, for instance, deliver in terms of delays in messages or answering timeouts, etc. Was that a consideration to impose more requirements on what the participant nodes have to behave like, or was that not a consideration at all in the design space?
I think it depends on the real system. So for example, the ETH, it is a purely synchronous network, and it requires the node has to, they are obliged, or they have to have a bottom line of the bandwidth or CPU resources. And if they do not fulfill their duty, they are punished, right? But actually, this only works for, like, the ETH is very big and mature, so a lot of nodes, they do not want to break down this ecosystem. But you have a relatively new or small network, then we are afraid that some minority of nodes, they do some bad thing, can break down this whole system. So that depends on the safety consideration and the ecosystem. I'm not sure if I answered your question.
All right, let's thank the speaker again.